Now that you've completed the introduction to design of experiments, let's start with our first design of experiments, a two-factor full factorial experiment. What we mean by that is there'll be two variables that we will vary between level settings, and we'll look at all possible combinations. So two factors at two level settings is going to be four possible combinations. Let's begin. We will illustrate our two-factor experiment with an example. In this example, let's start with what the problem is. We are faced with a transformer that's about the size of a dime that mounts on a printed circuit board that needs to have the inductance values raised. We measure inductance in millihenries. We need to increase the inductance value of the transformer, but we cannot exceed 20 millihenries. The objective is to figure out which factors and which settings are going to maximize our inductance values without exceeding 20 millihenries. So we have two critical factors that have been identified for the analysis. One is the number of turns in the winding, and the other is the gap distance between the ferrite cores. The number of turns is a quantitative factor, and we can measure that with a precision of 1 turn. We can also measure the gap distance with a precision of 1/1000th of an inch. After we've made our samples, we then test them. The measurement or the response that we are going to evaluate our experiment with is the inductance value. We will create a bunch of transformers at different settings of windings and gap distance, and we will measure the inductance values, and then we'll use our analysis of variance using our design of experiments method, which is structured to tell us which factor and which settings are going to give us the best readings to meet our goals. Let's take a look at our transformer so you can understand what the ferrite core is and what the windings are and what this beast looks like. Here is a picture that illustrates what our transformer looks like. We have a ferrite core on the left and the right hand side of the transformer. This ferrite core has windings of wire that are wrapped around it. The other variable is the distance that we have, this gap distance between the two halves of the ferrite core. That is a very simple transformer, but that is actually what we're dealing with here, a very simple transformer. It's significantly smaller than what you're looking at, but that's the gist of what we're dealing with. The following is our experimental definition and layout. For this two-factor experiment, we have factor A, which is the number of windings, and factor B, which is the gap distance. The low setting of factor A is denoted as A1, and that's 20 windings. The high setting of factor A, which is denoted as A2, is 30 windings. The low setting of factor B, the gap distance, B1, is 10/1000ths of an inch, and the high setting, B2, is 15/1000ths of an inch. Let's take a look at the values of inductance that we have achieved at the A1, B1 combination. So we're looking at a transformer that was built with 20 windings and a 10/1000ths gap. Here's the values of inductance from those 5 transformers. Next, we have the A2, B1 setting, which is 30 windings, a 10/1000ths gap. We built 5 more transformers, and here's the inductance values. At the A1, B2 combination, or 20 windings and 15/1000ths gap, we built 5 more transformers. And at the A2, B2 combination, 30 windings and 15/1000ths gap, we have another 5 transformers. So you see in each of these squared combinations that we have here, A1, B1 or A2, B1, you'll see the 5 values for inductance. The values that are in parentheses are just the sum of those 5 values for that intersecting combination. We'll use those totals when we go to calculate our analysis of variance. The overall totals that we have for A1 at its low setting is 154. So that is all of the values of inductance when A1 was at 20 windings. Then we have the A2 total, which is when the transformers were at 30 windings, we had a total of 123. So that's adding up all of the inductance values at 30 windings. Then we go across the experiment now, and let's get the total for B1 when we had a 10 thousandths gap, and we get a value of 169. So that is the total of all of the inductance values when we had a transformer at a 10 thousandths gap. The last one we have is transformers that were built with a 15 thousandths gap, and that total turns out to be 108. Now the overall grand total of all of the inductance values, which we will need in our analysis, is a total of 277. Now one of the things that we do when we build our sum of squares to do our analysis of variance, we need these totals. So let's move on to the analysis of variance, and you can see how we'll use these totals to calculate the analysis of variance for each one of the factors. In essence, we're doing a hypothesis test on number of windings. We're going to do a hypothesis test on gap distance, and then we'll do a hypothesis test that's associated with the number of windings and gap distance combined effect, or what we call an interaction. So let's move forward and take a look at the analysis of variance. To begin our analysis of variance, we will first calculate the sum of squares. The sum of squares represents the total variation that we saw in all of the data associated with our experiment. So here's the data from all combinations of windings and gap distance. The first calculation is the total sum of squares. This is the most difficult calculation that you'll be faced with. We will use each individual value to calculate the total sum of squares. Each individual value is squared and added together. We then subtract away what we call the correction factor for the mean, which is the total of all the data points, a value of 277 that we can get from our table. We square that value and divide by the total number of data points. In this case, we had 5 transformers built per combination, and there were 4 possible combinations. So we had a total number of data points of 20, or 20 transformers were built that we evaluated. When we finish this calculation, we see that the total sum of squares, which represents all of the variation that we had in our experiment, was equal to 250.55. We next want to find out how much of that sum of squares, or variation, was associated with A1 and A2, the number of windings changing from 20 to 30. Then we're going to calculate the sum of squares associated with the gap distance. What happened when we changed the gap distance from 10 thousandths to 15 thousandths? Those sum of squares should chew up a good portion of that 250. Let's hope that it does. Let's start with factor A, which is the number of windings. Its totals for A1 and A2 were 154 and 123. We take the difference between those totals for the low setting and the high setting, we square that and divide it by 20. That gives us a measure of the sum of squares for factor A, which tells us how much variation was caused when we changed from 20 windings to 30 windings. Next, we'll take a look at the gap distance. When factor B went from 10 thousandths to 15 thousandths, the variability is associated with those totals. We see that for B1 it's 169, and for B2 it's 108. We take the difference between those totals, we square it, we divide by the total number of data points, and that gives us a value of 186. So we had 250 was the total sum of squares. 48 was associated with factor A, 186 was associated with factor B. There's still some left over, so let's find out how much was associated with the interaction between A and B, the combined effect of those two things, and then what's left over, which is going to be our residual. Now we'll continue with our sum of squares calculations. One of the things that we're concerned about is an interaction. It's a special combined effect of two factors. When two things work together, like time and temperature and pressure. Well, in this case, we're going to evaluate if windings and gap distance have a relationship or a combined effect. So that's going to be an interaction, if it exists. We denote that by A cross B, or A times B. A significant interaction can sometimes suggest the selection of different settings than what the main factors tell us we should select. The main factors would be the single effects taken alone, which would be just the difference between the low and high settings for the number of windings, or just the difference between the low and high settings for the gap distance. The combined effect is going to allow us to look at what happened when each of these two things changed and the combined effects when they were working together. Let's take a look at our data table. So the sum of squares in an interaction is going to be associated with the combined effects. So we're actually going to be looking at the data at the intersection of some of these combined effects, like what happened when A1 and B1 were working together, or what happened when A2 and B1 were working together, or A1 and B2, or A2 and B2. So we'll actually be looking at the intersections of those and gathering that information to calculate our sum of squares. So the sum of squares for the interaction uses the following equation. So this way we're looking at the cross relationships between the interactions, or the intersections that we see in our table. So the data points that we're going to be using are those totals for each of those groups of 5. For the A1B1 total and the A2B1 total, the A1B2 total, and the A2B2 total. So instead of the full column or the full row being evaluated, like we did when we looked at windings and gap distance, now we're looking at the individual combinations of windings and gap distance taken individually. So we see that the sum of squares for A times B, or the interaction of A and B, was a value of 6.05. It is a small value, but it's an incremental effect that would sit on top of the main factors effects. We will have to look at our analysis of variance to find out if that value of sum of squares is significant or not. The remaining sum of squares, after we've taken away the sum of squares for factor A, factor B, and the interaction, leaves us with a residual or leftover sum of squares of 10.4. We'll also have to take a look at that in our analysis of variance to find out if that's a small enough value that we can deem that our experiment is a good experiment. Our next calculation from the original data is the degrees of freedom. This gives us a measure of the power of our test. We start with our total degrees of freedom. The total degrees of freedom is calculated by subtracting 1 away from the total number of data points. We're going to be doing an analysis, so we have to pay for it. So we take the total number of data points, which is 20, we subtract away 1, we're going to pay, leaving us with a total degrees of freedom that we can work with our analysis of variance of 19. Factors A and factors B, the number of windings, and the gap distance, each had 2 level settings. We have 2 level settings, minus 1, because we have to pay for doing the analysis of variance. So that means that we have 1 degree of freedom associated with factor A and 1 degree of freedom associated with factor B. Note that the small a and b is the number of settings for factors A and factors B. The interaction, or the combined effect of A times B, or A cross B, we just multiply the degrees of freedom for A times the degrees of freedom for B to get the degrees of freedom for the combined effect, or the interaction. So that's going to be 1 times 1, which is going to be equal to 1. So now we've used up 3 degrees of freedom of our total 19 for our factors in our interaction. So the leftover or residual degrees of freedom, which is part of our bank account, which cannot go to 0, it's going to be 19 minus 3, leaving us with 16 degrees of freedom for a residual. So now we'll be able to conduct our analysis of variance because we have plenty of data points, which allows us to have plenty of degrees of freedom to conduct our analysis of variance. The next thing we have to calculate is the mean square, which is also denoted as the variance. This is a relatively simple calculation in this experiment because we only have 1 degree of freedom for the factors. So the total mean square is the total sum of squares divided by the total degrees of freedom, or 250 divided by 19. Factor A and factor B, their sum of squares divided by their degrees of freedom, which is just dividing by 1. The interaction is the total sum of squares of the interaction divided by its degrees of freedom divided by 1. So the sum of squares is actually equal to the mean square, or the variance, in this particular case, because there's only 1 degree of freedom for the factors and for the interaction. And the last thing we have to take a look at is the residual, and the residual sum of squares divided by its degrees of freedom gives us a mean square for the residual less than 1, a value of 0.65. We'll then use those values to continue on with our analysis of variance. Our next calculation in our analysis of variance is the F ratio. We'll calculate an F ratio, or an F statistic, for factor A, for factor B, and the interaction of A and B. This calculation is the mean square for the factor divided by the mean square for the residual. We would like to see this value be much greater than 1. In this case, we see that that's true, and what we're going to do is compare these calculated values versus the values from a table. Now, the F distribution, there's an infinite number of distributions for F ratio values, and those distributions are associated with the degrees of freedom for the factor and the degrees of freedom for the residual. The table values are typically broken into p-values that are associated with 0.05 or a 95% confidence, or p-values of 0.01 or a 99% confidence. We're going to look up the F statistics associated with a 99% confidence, or the F statistics that would be associated with a p-value of 0.01. So we look up the table, and for 1 degree of freedom per factor and 16 degrees of freedom for the residual, at a 99% confidence, or a p-value of 0.01, we see that the F ratio has a value of 8.53. We're going to compare that ratio from the table, that value, against the ones that we calculated. Now, the values that we calculated are all larger than the value from the table. That tells us that factors A, factors B, and the interaction of A and B are all significant at least a p-value of 0.01 or a 99% confidence. So if our calculated F statistics, or F ratios, are larger than the value that we look up in the table, then we can conclude that they are significant, that there is a difference when we change between one setting and the other setting for factors A, B, and the interaction of A times B. Let's review our F ratio tests. When we compare the values that we calculated for F ratios against the table values, as long as the F ratios that we calculated are larger than the table values, then we can say that there is a significant difference when any one of our factors or the interaction change their level settings. In this case, we took a look at the F ratios from the table that were associated with a significance level, a p-value of 0.01. That means that we have 1 minus p, or a 99% confidence. That table value is associated with 1 degree of freedom for the factor, 16 degrees of freedom for the residual, and the value that we got from the table for a p-value of 0.01 is a value of 8.53. Factor A, factor B, and the interaction of A times B all have calculated F ratios that are larger than the value from the table. Because of this, we can conclude that all of these factors and the interaction are significant. That means that factor A, number of windings, when it changed between 20 and 30, it made a difference. Factor B, the gap distance, when it changed between 10 thousandths and 15 thousandths, it made a difference. And also the combined effect of windings and gap distance, when those changed together, it made a difference as well. So everything in this particular experiment is significant. We use the p-value significance to help us understand if the factors, when they change between levels, are guilty beyond a shadow of a doubt. In this case, we use table values associated with a level of significance of 0.01 or 99% confidence. It's telling us that there's less than 1% chance that there isn't a difference in the inductance values when the number of windings or the gap distance changed. Software packages are available that will calculate the exact p-value, and that could be OpenOffice.org, Calc, it could be Excel, or it could be Minitab, or JMP from SAS Institute. They will all give you the exact p-value. If we calculated the exact p-value for factors A, B, and the interaction, we'd see that they're all less than 0.01. Typically, if we were just to use table values, we use table values for 0.01 and 0.05. There are other values that could be used, but those are the standards, a 99% and a 95% confidence. We have a lot of confidence in the results of this experiment. These factors are guilty of changing the inductance value when they change settings beyond a shadow of a doubt. The pure sum of squares is a concept that was developed by Dr. Junichi Tauchi. The pure sum of squares takes into consideration the uncertainty due to the residual or the unexplained variability. So what we're doing in essence is we're taking the sum of squares and we're reducing it by a factor associated with the mean square for the residual. Any of those pieces that we take away from the sum of squares for the factors gets added back into the sum of squares for the residual. So in essence what we're doing is we're reducing the size of the sum of squares for each of the factors and the interaction, and then the pieces of the mean square for the residual that we're taking away from them are being added back into the residual, and the sum of squares for the residual gets inflated. So we deflate the factors sum of squares and we inflate the residual sum of squares, so this way we can take into consideration any of the uncertainty due to the unexplained variability. This allows us to then calculate a percent contribution, or what's called a rho percent, for the sum of squares. So the total sum of squares, whether it's pure sum of squares or just the regular sum of squares, is equal. The only difference is the mean square for the residual, which is subtracted away from the sum of squares for the factors, but is then added back into the sum of squares for the residual. We can then look at the percent contribution of the pure sum of squares. This gives us a measure of the percent of the variation that's associated with the changes that take place between level settings for a factor or an interaction. We also look at the residual sum rho percent, and we would expect that to be something less than 50%. If the residual percent contribution or the unexplained percent contribution is 50% or less, then we can say that this experiment was successful. This was a method that was incorporated by Junichi Taguchi so that we would have a means to evaluate how much of the variation is explained without necessarily just looking at the p-values or the F statistics. We always like to think of things as a percent contribution. When we calculate the R value and the R squared value in a regression analysis, the R squared gives us the percent contribution associated with a variable's impact on the regression equation. This percent contribution based on the pure sum of squares is doing the same thing for us. Now that you've seen how to put together all of the components of the analysis of variance, let's group them up into an ANOVA table and see if we can review the results for the transformer experiment. The first thing we do is we start with a column for source of variability. We had factor A, which was the number of windings, factor B, which was the gap distance, the interaction of A times B, we have the residual, and then a totals. The first thing we calculate from our data set is the degrees of freedom. We had 20 total data points. We take away 1, giving us a total of 19 degrees of freedom. Factor A, B, and the interaction all had 2 level settings, so they receive 1 degree of freedom. That leaves us with 16 degrees of freedom for the residual. The sum of squares is calculated from the data itself. The degrees of freedom and sum of squares are the only two things that are calculated from the data from the experiment. Everything else that is in this analysis of variance table is calculated from the rest of the table. The mean square is just the sum of squares divided by the degrees of freedom. The F statistic that we calculate is the mean square divided by the mean square for the residual. Then we can take a look at the significance. We look up some values in our table and we can see that we have values for the significance of 0.01 or a 99% confidence of 8.53. The table value for a p-value of 0.05 or a 95% confidence is 4.49. All of our calculated F statistics are greater than the 4.49 and they're also greater than the 8.53. So we can say that they are significant at a 99% confidence or a p-value of 0.01. The pure sum of squares allows us to calculate the row percent. The pure sum of squares is just the sum of squares for a factor less its degrees of freedom times the mean square for the residual. The sum of squares for the residual would be its sum of squares plus the degrees of freedom for the factors, all of them added together, times the mean square for the residual. So in this case, it would be the 10.4 plus 3 times 0.65, giving us a value of 12.35. So you can see that we've deflated the sum of squares for the factors and inflated the sum of squares for the residual. Now we go ahead and calculate our row percents. We can see that factor A accounted for 18.9% of the variation when it changed from 20 windings to 30 windings. Factor B, the gap distance, when we went from 10 thousandths to 15 thousandths gap, that accounted for 74% of the variability. The interaction picked up an additional 2%. The residual, 4.93%, is much less than 50%, so we would say that our experiment was successful. With all of this put together, we can conclude that factor A, factor B, and the interaction of A times B are significant. Now that we've finished our analysis of variance, we know that we've got a good experiment, and we know that we have some significant factors. In this case, factor A, factor B, and the interaction of A and B are significant. The next step is to determine what is the best level setting for those factors. So for windings, factor A, the low setting, A1, gave us the highest inductance value on average. We would select A1. Factor B, the gap distance. The low setting, B1, gave us the highest average inductance value. We would select B1. And when we look at the interactions of A and B, we see that the A1-B1 combination gave us the highest inductance value of 19. We would select that as well. The overall total average was 13.85. So of all the variation that we saw, regardless of the level setting of the factors or of the interaction combinations, the overall average of inductance was 13.85. We are going to see a significant improvement over that average based on choosing the best level settings that we have from our significant factors. Let's interpret our interaction. We can plot a graph where we put A1 and A2 on one axis. We have the values of inductance on the y-axis. B1 is our red line. B2 is our black line. If we focus on the A1-B1 combination, we can see that we end up with an inductance value of 19 on average. And that's our best setting. When isolating on B2, a wider gap distance, we see that as we change the number of windings, there's not much of an effect. But if we isolate on B1, the tighter gap distance, we can see that as we increase the number of windings, there's a more noticeable effect on the inductance value. So at that level of gap, it's more susceptible to changes in the number of windings. That's what an interaction is all about. Now if we look at this plot, if we extended these lines, we'd see that they would intersect. If we had a plot where the lines tend to look like they're going to be parallel and they'll never intersect, then we're not going to have a strong relationship in the interaction. Now that we have found out the factors that are significant and we've looked at the best level settings, we need to make a prediction as to what we're going to gain from this experimental outcome. Since the interaction of factors A and B tested to be significant, it takes precedent over factors A or B taken alone. The combined effect is always more significant and takes precedent if it turns out to be an important variable based on the p-values in our analysis of variance. It is an incremental effect on top of the main effects of A and B. So in this case, the A1-B1 combined effect gave us an inductance value of 19. That was the highest inductance value. It's less than 20, but it's almost 20, and that's what we were trying to do, get as close to 20 as we could without exceeding 20. So our calculation for our prediction is to take the overall average from the experiment and then add to it the sum of the best settings or interaction with the overall average subtracted away from it. So basically what we're doing is what's the incremental bump from our best setting and its difference between the overall average of the experiment. In this case, you can do this by inspection because the t average values, the t bar, those are going to drop out of the equation, so our prediction is going to be 19 millihenries. Notice that if we use the main factors instead of the interaction, our prediction would be less than what the actual value is going to be. We also have some instances where the main effects give us opposite selections for best setting that are different than what the combined effect or the interaction would give us. So we have to watch out for those. That's why if an interaction turns out to be significant based on the F statistics and the p-value, then that takes precedent over the single effects taken alone. Now, to confirm the results, we would build some transformers with 20 windings and a gap distance of 10 thousandths, measure the inductance, and compare it to the predicted condition. That validates and verifies that our design experiment has been successful. Let's review our analysis of variance table, and here's a summary of all the calculations. First, we have a column where we use the factorial effect, where that's the sources of our variation, our factors, and the residual with the totals. Next, we have the degrees of freedom. Level settings -1 for the factors is their degrees of freedom. The interaction is the degrees of freedom for each factor in that interaction multiplied against the other factor's degrees of freedom. And the total degrees of freedom is just the total of all the data points, n -1. We subtract away the factor degrees of freedom in the interaction, and we get the residual. Next, we have the sum of squares. These are calculated from the actual data in the experiment. The mean square is calculated by dividing the sum of squares by the degrees of freedom. The F statistic, or the F ratio, is the mean square divided by the mean square for the residual. Then we have the significant values. Those are calculated by either Excel or OpenOffice or Calc or Minitab or SAS Jump, or we can look them up in table values, and typically we use table values of a p-value of 0.01 or a 99% confidence, or a p-value of 0.05 and a 95% confidence to compare them against those F ratios that we calculated. Then we calculate the pure sum of squares, where we deflate the sum of squares based on a factor of the mean square for the residual, and we inflate the residual because we were taking into consideration the fact that there's uncertainty due to the unexplained, or the leftover, which is called the residual. Then we calculate the percent contribution, which is the percentage of variation that's associated with the sum of squares for any one of the factors or the residual. We'd like the residual sum of squares to be less than 50%. That's how you pull together the analysis of variance table with a summary of calculations. Now that we've conducted the analysis and we've done it pretty much by hand. Let's utilize one of the software packages. So let's open up Minitab, and two-factor DOE.mpj is the file to open. Once you open it, you will see that the worksheet will present the designed experiment in a manner such as this. Next, we will go to the Stat menu, to DOE, Factorial, and select Analyze the Factorial Design. Once you've done that, a dialog box will appear. Select Inductance for the response. Then we need to select Graphs. In Graphs, we'd like to have an effect plot called a Pareto, and we want to set the alpha at 0.05. You'll see why we're doing that once we get to that Pareto chart, but it'll help us to understand which variables are significant. Next, we want to select the terms. In this one, we're going to take a look at windings, which is our factor A, the gap distance, which is our factor B, and the A times B interaction. Once you've done that, select OK. Then, for the results, we want to have the coefficients in the ANOVA table. We can display the alias table, and then we want to make sure that the available terms have been moved over to the selected terms, which would be the windings, the gap, and the A times B interaction. Once you've done that, you can press OK, and then press OK once more, and then the first chart you will see will be that Pareto analysis. Here we have the effects plot Pareto. You'll see that we have factor B followed by A and the AB interaction. They are in order of the strength of their relationships to the values of inductance changing when we changed between level settings. The line that we see, the dotted red line, that line is associated with the fact that we said that our alpha is 0.05. That is equivalent to a p-value of 0.05. All of our factors are significant beyond the 95% confidence or p-value of 0.05 indication. So now we know that we're at least significant at a 95% confidence. Here we have our ANOVA table of the results from our design experiment. This can be found in the session window in Minitab. Notice that our ANOVA table, our analysis of variance, has our sources, our degrees of freedom, our sum of squares, our mean square, our F statistics or F ratio, and our p-values. When we take a look at the p-values, we can see that our main effects have a very, very small p-value. P-value is 0.000, which means our confidence is somewhere close to 100%. The two-way interactions have a p-value that's extremely small as well, 0.008, giving us a confidence of 99.2%. Therefore, we can conclude that the main effects and the two-way interaction are significant. Now that we know that the windings, the gap distance, and the interaction of windings time gap are significant, we can take a look at the average values for the different settings of those variables and see which average values are going to drive us toward the inductance value that we're trying to achieve. In this case, we're trying to maximize the inductance value without exceeding millihenries of 20. If we take a look at windings, it tells us that 20 windings is going to give us an average value of 15.4. We would select that because it has a higher inductance value than 30 windings. When we look at the gap distance, we can see that we want to be at 10 thousandths of an inch. That gives us a higher inductance value, 16.9, than we got when we were 15 thousandths. We can also take a look at our interaction, and we can see that the combined effect of 20 windings and a 10 thousandths gap gives us the highest value, 19. That's driving us close to that 20 millihenries, which is our goal. Using Minitab, we can also graph the results with a factorial plot. So we can take that data table that we had already just looked at in the session window, and we can generate some graphs. So to do that, we select Stat, DOE, Factorial, and then Factorial plots. The dialog box that comes up allows us to select whether we're going to plot main effects, interaction plot, or a cube plot. In this case, we're going to select the main effects so we can plot factors A and B, and then we're also going to select the interaction plot so we can plot that interaction of the combined effect of A times B. You have to push the setup button for the main effects plot, and that'll allow us to select the response that we're going to do our graph against. In this case, it's the inductance values. We take the available terms and we move them over to the selected terms, and in this case it's windings, factor A, and gap distance, factor B. You can also select the options button and give it a title. Once you've done that, click OK and OK, and then we need to set up the interaction. In the interaction setup, the response is also going to be inductance, and we want to have the interaction between factors A and B, so we need to select those by moving them from available to the selected window. We can also put a title on this by selecting options. When that dialog box comes up, we can add some text in there to say that this is going to be the interactions of winding and gap. Once we've done that, we can hit OK and OK, and then hit OK for factorial plots, and that will generate the graphs. Let's review the main effects factorial plot. We can see that we have windings and gap distance plotted. Let's take a look at the windings plot. It shows a windings number of 20 windings and 30 windings, and then we've plotted the average inductance values based on those settings of the factor windings, which is our factor A. We can see that when we're at 20 windings, we have the highest inductance value. When we look at the gap distance, we have settings of 10 thousandths and 15 thousandths. And notice that when we are at 10 thousandths, we have our highest inductance value. Notice also that the slope of the lines are a little bit different. The gap distance is much more vertical than the windings. It's a stronger factor, and we've seen that in our Pareto analysis and also in our F statistics. Here we have our interaction factorial plot. We have plotted the gap distance on the horizontal axis, 10 thousandths and 15 thousandths. On the y-axis, we have our average inductance values. The black line is for 20 windings, when we go from 15 thousandths to 10 thousandths in gap distance. The red line is for 30 windings, when we go from 15 thousandths to 10 thousandths gap distance. Notice that when we're at the larger gap, the changing in the number of windings doesn't make as big of a difference as when we're at the smaller gap. When we're at 10 thousandths of an inch gap, changing from 20 to 30 windings makes a large difference in the average inductance value. The best value is at 10 thousandths gap and 20 windings. That gives us the highest inductance value that's driving us toward our goal, which is to achieve as close to 20 millihenries as possible without exceeding 20 millihenries. To make a prediction using Minitab, we use the response optimizer. So to get to that, it would be stat, DOE, factorial, and then select response optimizer. Once you've done that, the dialog box comes up and asks you to select the outcome or the response that you're going to be evaluating against. In this case, it is inductance. After you've selected inductance, then we can select setting up the response optimizer. We have a target, that is our goal. Our lower bound is 5. Our target is 19 with an upper bound of 20. Now that we have it set up, we can push the OK button and OK again, and the response optimizer will tell us the best settings to achieve our target. This is the output from the response optimizer. It's giving us a prediction and the best settings. The best settings are 20 windings with a 10 thousandths gap. The Y value is what the prediction is, and it's predicting that we should hit a target value of 19. D is the desirability index, and that's at 100%. So that's what the response optimizer can give us when we have used it to evaluate our designed experiment. It's actually running off of a regression model. So we can go into the response optimizer and we could change the number of windings to 20, to 22, to 23. We could change the gap to anywhere between 10 and 15 thousandths, or the windings to anywhere between 20 and 30 windings, and it would then predict for us what the inductance values would be. So this becomes a powerful tool once we've conducted a designed experiment. And now for your exercise, the boiling water DOE. In this experiment, you are going to determine the settings of the container, whether it's covered or uncovered, and whether it's rotating or not rotating. What are the best settings that are going to minimize the time it takes to boil 1 cup of water in a microwave oven? Boiling water would be determined by the first signs of bubbles that we would see in our containers. So I would suggest that you use clear containers and use containers that are the same size. Let's take a look at the design, and after we've done that, we will create it using Minitab, and we'll walk you through how to do that. The boiling water DOE. You're going to use design of experiments to determine the best settings of 2 factors to boil water in a microwave oven. Your goal, minimize the time to boil 1 cup of water in a microwave. It should take you about an hour, maybe a little bit less. The factors and the settings. We're going to use the same size container. I would suggest you use a clear one. We're going to cover it, yes or no, and we're going to rotate it, yes or no. So this is a 2-factor, 2-setting, full factorial experiment, so we'll also be able to study the interaction of covering and rotating as well. You'll conduct the experiment after we've designed it in Minitab, analyze your results, make a prediction, and then validate those best settings in boiling time. We're going to set the microwave at a high setting of time and temperature. So set it on high, and then set the timer at about 7 minutes. It'll probably boil sooner than that, of course, but what we'll do is we'll subtract the time from when you start it and when you actually start to see the bubbles. I would convert the time into seconds instead of trying to say minutes and seconds. I would convert it all into seconds. So let's move on, and I'll take a look at how Minitab can be used to design this experiment that you can then conduct in your kitchen. We are now going to use Minitab to create the boiling water design of experiments. We start by selecting the stat pull-down, selecting DOE, Factorial, and then create a factorial design. When we begin to create the factorial design, it's going to give us a series of dialog boxes. We're going to have a 2-level factorial, which means we're going to have a low setting and a high setting. We're going to select the number of factors. There's going to be 2, whether it's covered or not, and whether it rotates or not. The designs that are available to us would be a full factorial with 4 runs. 2 factors at 2-level settings would be 4 possible combinations. Next, we'll enter the factors. Select the factors button, and it's going to give us factor A and factor B. We type in the name, we select from the pull-down, whether it's text or numeric, and then add the settings. We're going to use yes for low and no for high. Next, we have options. We're going to tell it not to fold the design. We're not going to check the randomized runs box. This way, our designs are going to look exactly the same, and we are going to store it in a worksheet. Generally, we randomize the runs, but in this exercise, let's have them all come out exactly the same so that what you get is what I'm going to show you. Next, we have results. We don't need any printed results, but we would like to have the default interactions. We're ready to generate the design. So click OK, and it'll put it into a worksheet. So here's what the design looks like. We have 4 experimental runs. The run order is the same as the standard order. We didn't randomize. We're going to cover and rotate. Those are our 2 factors. And you can see the 4 possible combinations that we have of the 2 factors at the 2 level settings. Next, we're going to add boiling time in seconds as column C7. That's our response. So after you set up the experimental condition, and the first one would be to cover it and to rotate it, then we would take a look at it through the microwave. Once we start to see the bubbles, then we'll be able to subtract the start time from the finish time and get the boiling time in seconds. Do that for each experimental condition, and then we'll be able to analyze it like you've learned how in the previous sections of this module. I hope you have fun with this. We're going to show you a video on how to create the design, and we're also going to show you a video on how to conduct the experiment in your kitchen. I hope you enjoy. This will be your first design experiment, and it's on your path to learning about some really cool tools to drive dramatic improvement in products and processes.